got a number of points I want to point out here. First of all is the town of Ritzville. If ever you've gone on Interstate 90 to Spokane, you've gone right through there. Further up Interstate 90 is the town of Sprague. Further down, if any of you are WSU students, you've gone to Pullman and you've traveled Highway 26 many times and gone by a little town called Hooper. It's a very important part of our story, and you'll see that in a little bit. Just west of that is the town of Washtuckna, where this program is being brought to you live from the town of Washtuckna, okay? So that's where I'm located. And then further down the coulee is Clotus. We've got some bodies of water that run through here. First of all, we have Sprague Lake. And again, if you've been on Interstate 90 and stopped at the rest area there, you've looked right down on it. And then on the west or on the east side, we have another lake called Rock Lake. In addition to the Snake River running through here, which you see at the bottom of your screen, we have the Palouse River that comes in from the east and flows on through the lower part of all this. Before the floods, the Palouse River flowed down through present-day Washtuckna, Clotus, on through Connell, Mesa, Eltopia, and finally entered the Columbia River down at the Tri-Cities. It never did enter the Snake River. But we've got this capture here, and the river ended up being about, taking a shortcut of about 50 miles from its old route. Also, coming out of Rock Lake, we have Rock Creek, and out of Sprague Lake, we have Cow Creek. Cow Creek enters the Palouse River down here at Hooper. Now, one would think that on this divide, this channel across here, by the way, is as much as 26 miles wide, this flood path. And these lighter areas are the fields that are being farmed mostly for wheat. And the darker areas are the areas that have been where the soil's been washed away. And there's still some remnants of Palouse soil out there in the middle. And one would think, well, it's really easy to figure out where the flood routes went. I'm going to put in the borders there of the scabland tract in yellow. But one would think that you could kind of divide this into the west side, which is the Cow Creek drainage area, and the east side, which is the Rock Creek drainage area. And that would be nice and simple. But nature isn't always that simple, because we've got water spilling over from the Cow Creek side into the Rock Creek side. And then we got water spilling back over from the Rock Creek side, back over to the Cow Creek side. And we have this anastomosing drainage on a very large scale. And the point is, we've got water everywhere. In fact, up on the top of your screen, there's another blue line I think I just put in there. And this is Crab Creek, which is part of the Crab Creek Tilford drainage scabland tract. But there was so much water coming down Crab Creek drainage that it spilled over into the Cheney-Palouse scabland tract. And there was so much water coming down the Cheney-Palouse scabland tract that some of it spilled back over into the Crab Creek in numerous places. The point is, we've got water everywhere. So if we look at the two main ingredients, first of all, we got to look at the Columbia River basalts. And these basalts, as you probably know, came out of fissures starting about 70 million years ago. And most of them were coming out of the corner area there of Oregon, Idaho, and southeast Washington. Over time, the later ones started in a path kind of going to the north or east here, right through the Cheney-Palouse scabland tract. And we're starting to find evidence of where those fissures are, and I'll show you some of that here in just a little bit. These fissure eruptions are much like we saw in Hawaii a couple of years ago, where we had that huge fountain that came up and spilled water or lava, and it floated itself down to the ocean. But instead of being a nice little channel, these just flooded out over many areas, and there were multiple fissures going on at the same time. And some of those as far as the Pacific Ocean. This is in one of the coulees, and actually right here, you can actually see one of these fissures coming up. This is one layer of basalt layer right here, one flow. Here's another flow above it, a little bit different color, and here you can actually see the fissure where that lava was coming out and then spilling out. Then later on, another one came over the top of it. This is taken in the lower Palouse Canyon, and we need to kind of understand basalt. The basalt comes from these lava formations that cool from the top down and from the bottom up. And because of that, we have two distinct major layers in each basalt flow. And there's a line I'm going to put in right there and another line there. So this top one, this is lava cooling from the top down. And this is lower part is the lava cooling from the bottom up. And then they meet and form a horizontal line in here. So we've got a horizontal weak position or layer right here, and then where the between the flows, we also have a horizontal weak area. And water can move pretty easily horizontally through basalt. It has a horrible time trying to move through it vertically. If I throw in the rest of these, we've got 1, 2, 3, 4, actually 5 flows exposed here. And we've got an elevation of 200 feet. So right here, these flows are averaging about 40 feet for each flow. The top part of the flow is called entablature. I lived with a geologist down in Oregon one time, and he was explaining that when this lava cools, it has kind of a real problem. It has to satisfy two things. One, it has to take up less space. And we all know as things cool down, they shrink. And so it has to take up less space. But the molecules in that lava also want to cling on to each other. They didn't want to cling on to each other. We just have nice round, like round pencils all over the place going up and down. But because they want to cling on to each other, it compromises and we get polygonal shapes. The lower part, which is called the colonnade, this is where we find these big, massive columns. They're 5, 6-sided, sometimes they're only 3, sometimes 4. But 5 and 6 seem to be the most common. And these are very vertical, straight up and down. The upper part, the entablature, it also has that same shape, but they're much smaller and they almost are like spaghetti that's intertwined around each other. So they really hold on to each other really well. In normal conditions, the entablature erodes the easiest because water gets in there, freezes, thaws, and discards the rock. But under big water volumes, the colonnade is actually eroded easier because those columns are easily plucked out because they're not interlocking. This is basalt, and we call it scoria. And this is one of those areas where we're starting to discover where some of these fissure eruptions were in the Cheney-Palouse Scatland tract. Once we started finding these things, we find more of them, and we get a better idea where these flood basalts were coming up. You'll notice we've got a vertical thing right here. And what basically this is if you can imagine that, visualize that volcanic eruption in Hawaii a couple years ago.
Lloyd, unmute yourself.
Did I just do that?
We got an audio deal going on here, but thank you, Lloyd.
How far back do I need to go?
About a minute.
Just about a minute.
Do I need to go back to the other slide?
No, you were talking about scoria.
Okay, well, I didn't lose much then. I got excited there and hit my button over here. Oh, the wonders of Zoom. Anyway, these fissure eruptions, if you remember in Hawaii, imagine that lava is being thrown up hundreds of feet in the air and then flopping out around to the sides and starting to solidify. And while it's still in that semi-molten stage and semi-solid stage, more lava is being forced up, and it's capturing some of that semi-molten rock and moving it around and moving around the side of that fissure. And that's why we start getting these types of structures in here. I found this just off the Palouse Canyon, just a little up ways up from Lyons Ferry several years ago. And I had both Eugene Keever, which most of you probably know, he looked at, and then also Chad Pritchard from EWU, a geologist up there, he also looked at, and they both agree that this is what we're finding here. So Chad came down one time and we looked and looked for the vent itself, but we couldn't find it. But we know we were really close here, and the vent apparently has been eroded away, and I'll kind of show you that later on. The other main element we have in this area is a wind-blown soil called loess. The first loess that blew into the area was probably from some of the erosion off the new Cascade Mountains that were rising. As those sediments were being washed out into the basin, they would get picked up and blown in. A professor from WSU a few years ago came up with the idea that really what's going on now is that we know there's been more than floods during the last glaciation. We're finding evidence that it's difficult to find, but we are finding flood gravels underneath the Palouse soil and other evidence that strongly suggests there were other ice age floods earlier than this last round. And his idea was that these floods would wash the Palouse soil, this loess, down to the Pasco Basin where it would settle out. The dry climate and the winds would blow it back up. And different episodes of these Palouse hills are layered just like the basalt is. It's not just one structure. They're definitely layered over a long period of time. And then another flood would come and wash some of the soil back down there, and then the next dry period would blow it back up. So you almost got a conveyor belt here of water washing it down, and then wind blowing it back up, and water washing it back down. And we still have some of that activity go on today. This was taken several years ago right outside my window of my house here. And this is one of these good dust storms that blows up from time to time. If any of you are meteorological nerds, it's really a good point to look at the front leading edge of a cold front. This is, as this cold air moves in, it forces itself underneath the warmer air, and that warmer air rises up, and that's what causes all this uplift of this loess. So those two ingredients make up most of it. But we do have a few other things. Sometimes between basalt lava flows, there were thousands of years, and that gave time for soils to form, lakes to form. And so once in a while, we find these intersedimentary beds between the basalt layers. And this is one that's just, 100 or 200 yards up from Palouse Falls in the canyon. This is Chad Pritchard getting all excited because explaining what's going on here. But this is this sedimentary layer down below, and right above it is the columnar basalt, the colonnade. What's interesting, if you go right to this spot where those two guys are standing and look straight up the edge of the canyon, you look up into the entablature, and you can see all of those. Again, there's a polygonal shape up here, but they're much smaller than you see in the colonnade down below. We also have some erratics in channel scablands over here. This is not basalt, this is granite. It's not the young lady up there, she's not erratic. She's actually a post-grad student from UMass that was out here a couple summers ago doing research on erratics in the channel scablands. And there's apparently new technology out there where they can actually take samples off of this rock and process it chemically. And the changes in that can pinpoint real close the date that this rock was deposited here when it was exposed. And so she was taking samples from rocks throughout the area. This little rock is near Cow Creek. And actually, if you know where it is, you can actually see it from on Google Earth. This rock was originally bigger, but this site over here was quarried for one of the earlier settlers in the area for his house, for his foundation. These erratics were ice rafted down during the Missoula floods on icebergs. And those icebergs got stranded out here, and as they melted, then they dropped off their load, or as the iceberg was rolling around and got broke up, the rock would come out. And so we do have some pretty good erratics over in our area. So that's our two main ingredients. So I think we'll just pause here for a minute and open it up for questions. I'm not a geologist by trade. I'm more of a geomorphologist, so don't get too technical on me on the geology questions.
You're welcome to hit your space bar, or if you want to type them in the chat window, either way.
I have one question. Is there any way that we could get someone to do that same kind of analysis in dating some rocks? We got some giant erratics on Whidbey Island. And the thought is that they are fairly recent, you know, from the last glaciation, but be good to know, be able to pinpoint a little more of, you know, how old they are.
Dale, do you know anything about how to do that?
No, you got me.
Okay. Why don't you give this gentleman my email address, and then I can forward the information I got from Karen, who's a young lady there, and she might be able to help you out as far as if there's anybody for this area that's doing it. It's a fairly new technology that they're using, but it's kind of exciting because, you know, we kind of know when the floods came through, but to pinpoint exactly when that rock was deposited there is exciting.
Yeah, it'd be nice to know if it was sort of early on in the deglaciation or, you know, towards the very end. Because the one I'm thinking of is one in Langley that is just absolutely enormous. I think Whidbey Island probably has the world's collection of biggest erratics. Nothing on Greenland or even Antarctica compares in size with what we've got on beautiful Whidbey Island.
Yeah.
And it'd be nice to get some dates because right now we don't. We just have these big rocks lying around and we don't know much about their history.
Yeah, she took samples there along Cow Creek, several erratics there, plus some down at the confluence of the Palouse and Snake River, and she also took some out of Grand Coulee. All right, well, I'm going to go ahead and continue. If there's any questions to think of, we'll come back to them later.
Yeah.
Coulees are kind of an interesting thing. They're what make up much of our area. And I discovered that geologists and geomorphologists have a wide range of what defines a coulee. They kind of all agree that they have a flat bottom, but some of them say that they're box-shaped. They're pretty adamant on that. Some say they're long, some say they're dry, some say they have a cataract in them. But you know, when I go over to our area, this is McElroy Coulee, which is just south of Ritzville, and it's got a flat bottom on it, but there's no way I would call this box shape. The sides are very, very sloping. I go down to West Technic Coulees, this is actually between Connell and Colotis. This was where the Palouse River used to run through before it got diverted. Well, it has a flat bottom, but the sides are more stair-stepped. And so I don't think you can just say they're box-shaped or they're sloped or they're stair-stepped. You find all of this in here. Are they dry? Well, what do you call this? This is actually Cow Creek running through here. We're looking up Cow Creek towards Sprague Lake, somewhere way off in the distance. We have the flat bottom again. But we got Scatland all the way across here. We got sloped here, and we got Box Canyon here. We got, you know, and we got water running through it. This is Cow Creek. So is this a valley or is it a coulee? Some people get creative and call it a valley coulee or a canyon coulee or whatever. I kind of go along with the idea that coulees can have water in them, but they're always an underfit stream, as this one is, or an intermittent stream. So I've come up with my own definition of a coulee, and it's real simple. I just say it's an abandoned ice age flood channel, which typically has a flat bottom. And I don't get into all those other things that people think they need to define. Here we got box shaped on this side, we got stair stepped on this side, and here we got a slope shape. And this is a huge gravel bar in Washtekna Coulee. And notice the giant ripple marks or current marks on it. We have a number of these in the Washtekna Coulee between Washtekna and Connell. Even on the floor of the coulee, there are ripple marks. They're not as pronounced, but they're also on the floor as well. Any questions about coulees? Like I say, I've got a whole nother program just on coulees. All right. So we're going to go back to our main map now. We're going to go into figuring out how it is possible that this capture occurred down here near Vernon and Palouse River. First of all, we're going to go up and look at the Rock Creek site. We'll get in here really close and highlight that area. They got Rock Creek, and Rock Creek enters out of Rock Lake just off the screen here. And of course, we got a flow going that way, but we've also got, there's so much water coming down Rock Creek that water is spilling over in 4 different coulees, taking a shortcut to the Palouse River. And we're going to take a quick look at all 4 of these things. Big Cove is the furthest one to the east where water first entered the Palouse River. And it has a recessional cataract in it. It started when that water first washed into the Palouse River. It started undercutting and worked its way upstream, cutting this real nice box-shaped coulee. Over to the west, just barely over the hill, we've got Little Cove. And this is looking down. The Palouse River is down here somewhere. It's kind of hidden, but it's down there, believe me. And again, this is a retreating cataract type situation. We get over to Mason Draw, and now it's not quite as spectacular, but we got a coulee running through here without any cataract in it. And this connects all the way through. And our last one is Texas Draw, which is the biggest of them. And again, we got the flat bottom, and we got the slope sides. And this is mainly because, you know, you're cutting out down to the rock, and the bluff stays off to the side here and cuts in. As the one of the questions we get asked is, how is it possible that this Palouse soil stays there, and yet we're getting all this erosion in the rock and the floor of the coulee? And the reason for this is going back to that structure of the basalt. Basalt is fractured as it cools, and it's also layered, and so it's blocky in nature. It's a very hard rock, but it's blocky. And therefore, when that water starts going across here and works its way down through the loess, once it hits that rock, that rough surface, it starts getting very turbid, very turbulent. And it starts plucking those blocks of basalt out. And as it pulls more of those blocks out, it gets even more and more turbid and even has more energy to pluck out even more. Off to the side, that water going by the Palouse soil, that's made up of really fine silt. And so that water goes by really, really easily and doesn't have hardly any turbidity to it as it goes by. So the Palouse hills, which are actually a lot softer, stay put. They erode back, but a lot slower. But the bottom of the coulee, once it gets down to that rock, it just starts eroding straight down. If we look at the Palouse River, this is what it kind of would have looked like before the floods came through. Just a nice, peaceful river valley, meandering around through the basalt. Off in the distance is Steptoe Butte. Further downstream, we still have this nice river valley, just nice and peaceful, nice, everything's to the right shape and size with everything. It's wonderful. But once we get down to where the Palouse River and Rock Creek join, we see a whole different picture. Looking up Rock Creek, we have this really wide area here. Palouse River coming in, again, it's a wide, wide area. I talked about Texas draw here, that coulee, that furthest west coulee. Well, there it is, way off in the distance. That's the opening of Texas draw. You start getting to see the immensity of what's going on over here. A lot of water is coming through here. If we go down to ground level and look at the confluence of those two rivers again, we got a very flat bottom, but it's a whole lot bigger than what we saw just up river a little ways. 6 miles up river, we got a nice valley. Here we got this coulee with a wide flat bottom. And way off in the distance there where my arrow is, that's actually the top of a less hill. And that's at least 4 miles back from the edge of the coulee over here. So this water coming through was not just flooding out the valley that it was in and cutting back, but it was going out beyond miles in both directions. A vast amount of water. So we looked at the Rock Creek area. Now we're going to go down and look at the lower end of the Cow Creek area. And there we are, and we've got floodwaters coming down Cow Creek, and we got floodwaters coming down the Palouse River now, which has been joined by Cow Creek. And they all meet right up here at ground zero at the little town of Hooper. We've got so much water coming down Cow Creek drainage that some of it is spilling out to the west, out in an area called Rattlesnake Flats. And it comes down through an area called the Staircase Rapids. If you ever leave Washington and head north, you go right up through there. This upper rim down to the coulee floor is about an 800-foot drop of 6 miles. And this area is called kind of been defined as a dry rapids, not a dry falls, but a dry rapids. And the hydrologists that have studied this estimate the water coming down through the Staircase Rapids was traveling about 70 miles an hour. There's so much water coming across there that some of it even spills out further to the west and cuts out Collier Coulee. And we'll look at that again in a little bit. There's also water spilling across this Palouse upland in several areas. And not only that, we're getting all this overflow from the Cow Creek or from the Rock Creek side coming back over the Cow Creek side. It all joins in here too. So hopefully by now, I have convinced you that there's a lot of water coming down here. And here we go. So we've looked at that part of the flood. Now we're going to go down to where everything kind of came together. And that's the actual divide between the Palouse River and the Snake River. In this area called the Palouse Snake River Divide. And we'll focus in on that. And if we put in our boundaries of where the major floods were, this is what we've got. We've got the water meeting here at Hooper. And yes, a lot of it does continue on down through the old Palouse River Valley, which is now Washtucknacoolie. But there's so much water coming down here at Hooper that you basically have two gigantic floods joining right there at Hooper. And there's no way in the world that old Palouse River Valley is going to hold all that water. And it spills across the divide like so and enters the Snake River down here. This opening up here is about 10 miles wide. There's 80 to 100 square miles of Palouse soil that has been ripped off and washed away. There's also some spillover from here that goes back this way. And I talked about Collier Coulee a little bit ago. If ever you've taken this road to Washtuckna and beyond, before you get to Washtuckna, you go down through two little coulees. Well, those are the two parts of Collier Coulee that split up above, but come back together further downstream and then join back into Washtuckna Coulee. This is not natural to have this sort of thing. You can only have this type of division with a lot of water. Further downstream at Clotis, we have another breach across the divide, and this cut out Devil's Canyon. And we'll take a look at that as well. So I think I'm getting, hopefully, my point that one of our elements is we had to have a lot of water in order to have that divide. If we go back up to Hooper, the Palouse River flows down right through here. Can't see it, but that's where it is. And we're looking up Cow Creek. And that's a pretty impressive opening up there, all this water is coming down. But if we stand back a little way, that's the area we were just looking at. And if you go over here, you can see the Palouse soil on this side, and way over here, you see the Palouse side, Palouse soil here. That distance across there is 4 miles. The hydrologists that have studied this have calculated that down in this part, just coming down the Cow Creek drainage, there was equivalent of over 200 Columbia rivers. Over 200 Columbia rivers, that's a lot of water. There hasn't been any studies that I know of yet that have calculated how much was coming down the Palouse River side of that Hooper. But I would expect is about the same. Well, all that water started spilling across the divide like so. Water coming down the Palouse River, Cow Creek, Hooper's just down over the hill there. There's about 350 feet difference between the base or the bottom of the coulee here and the top of the Palouse soil that it had to cut out. This is a Palouse Island, and these are remnants of that Palouse soil that stretched all the way across the divide. They're also called Less Islands. This is probably as good of a classic textbook example as you'll find. They've got a kind of prow on the front side on the leading edge, and then as you go downstream, they taper down and taper down. They kind of look like a giant tadpole swimming upstream. This is the eastern edge of the spillway, and it cut out and made this beautiful Palouse scarp along this side. We're going to go now 10 miles to the west and look down the west side of the spillway. This prominent peak right here, which is almost 200 feet high, they call it North Point, and it's a good reference point for a lot of things that we see down in this area. And again, you got this water spilling across the divide, working its way down to the Snake River over here. But you also have water still going down the old Palouse River Valley and spilling out. And at this point, we're 2 miles south of the old Palouse River Valley, or Washtuckna-Coulee as it is today. So again, we've got a lot of water to contend with here. If we look at a map of the area, here we've got the east side, and there's probably the Palouse Island we were looking at. Got the west spillway over here, and there's North Point. Palouse River coming in, the old flow this way, and here's where we're going here. And if you look at this map, you start seeing some real linear stuff going on. And this gets us into the second factor we have to have in order to have this divide. This first 4 miles of the Palouse River Canyon is straight. And that's not real common in nature to have a feature like that. What I'm going to do, I'm going to highlight that in blue. As you look around, there's more straight lines that more or less parallel that. This is part of a canyon called Wind Lake Canyon. This is the HU Canyon. And then there's smaller ones too that we see going the same direction. But there's another prominent direction, which I'll highlight in red. And there's an, excuse me. There's another prominent direction that I'm going to highlight in green. Years ago, when I was in college, the thought was that these were cooling fractures, but they've kind of discarded that now, and they've gone more to thinking that these fractures were caused tectonically. And that is that underneath the basalt, there was some earthquake activity, probably a slip slide where one block slides alongside the other one. And right there is that joint where that movement was. Gene Kiever kind of explains it really well. He says, just imagine putting a multi-layered cake on 2 boards that are right side by side. And what happens if you slide one of those boards alongside the other one? Well, that cake wants to go along with on the board that it is, and you get a crack right there where the movement is. And they've actually done, you can take a box, you can make a box with 2 bottoms in it and fill it up with clay. And then as you push the one board, you immediately get a crack right above where those 2 boards are moving side by side. You move it some more, and then you start getting these cracks coming out to the side. It's the same pattern that we see here. In fact, the angle between the blue direction and the red is the same angle as the blue and the green. With the clay, the angle isn't as great. So the harder the material, the greater the angle. But you can replicate this using clay in a divided box. One thing that I found kind of interesting is that we pick up the same green direction and the red direction in Ouachita Coulee, or the old Palouse River Valley, which makes you start thinking, well, is it possible that that was kind of the leading factor that got the river going where it went in the first place? Don't know for sure, but it's just an idea. So if we get up in the air and we look down the upper part of the Palouse Canyon, this is that 4-mile stretch from Ouachita Coulee going south. This waterfalls here is called Little Palouse Falls. Again, you notice the lake right here, perched right up on the edge, and yet water just does not want to go vertically through the basalt very easily, and that there's evidence because there's lakes all over the divide here. If we go down south now and look up the canyon, we get this other view. So Little Falls is up here now, and the Ouachita Coulee is right here. And now you can really start picking up these lines, and these are called fracture zones. If you can imagine that when these earthquakes happened, this tectonic started going, and you started moving that basalt alongside each other and fracturing this rock. Excuse me. When you fracture this rock, it's almost as if you're going in there and drilling holes and then dynamiting it. You're pre-quarrying this rock. So you've got these really weak zones in there with all these this rock that's all broken up and it's just sitting there. But once that floodwater came across the divide, it could easily pluck that rock out. Because of the volume of the water, it would pluck that rock out and wash it away. So that's our second part of why the river changed course. If we had just a huge flood and this was coming across granite or sandstone or some other rock, it would have crossed the divide, but the river probably would have never changed place. If we had just a fractured rock there, but no huge volume of water, it would still be covered with lusk today. And we wouldn't have the canyon and the river change. And there's our blue direction again. And our green direction. This is Rock Lake right here, or not Rock Lake, it's Long Lake Canyon. And there's actually a long lake down here. And this canyon actually curves a little bit up at the end of it, but for the most part, it's straight. And notice how many of these you can pick up on both sides of the canyon. And then we'll get the red direction in there too. And that even determines where the Palouse River starts zigzagging before it gets to the falls. If we look down the lower Palouse Canyon, again, we can really start seeing these fractures that go clear across on both sides of the canyon. This is Wind Lake Canyon coming in here. And Palouse Falls is right there in Palouse Falls State Park. Snake River flows left to right. Some of you may have been to Lions Ferry. This is where that scoria was found that I showed you early in the program. And you notice it's right in one of these fracture zones. When Chad Pritchard came down, I took him to look at this. I asked him, is it possible that these fracture zones is where some of these vents actually came up and the lava spilled out? And he says, well, it's possible because that would have been a weak area that the lava could have come up through. And the fact that we found scoria there indicates that there was a vent there, but because it was all broken up rock, most of it got taken away, and we found a remnant in there of that scoria, but not the dike itself. Marmas Rock Shelter, you may be familiar with that. In the 1960s, Dr. Dougherty from WSU did excavation work down here, and at that time they found marmoset men, or bones from that area, and at that time it was the oldest human remains that had been discovered in North America. Since then they found some that are older, but at that time it was the oldest. We go to the west side of the divide again. There's North Point up in the distance, so now we're looking up the west side, and this is the HU Canyon. If you've ever been to Palouse Falls, you've probably gone down and you've gone through a canyon, you switched back and forth and went through kind of a pretty impressive canyon. Well, you missed the main part right over here. This dry falls here is 280 feet high and would be nearly 100 feet higher than Palouse Falls. And again, HU Canyon follows that blue direction and the upper part follows the red direction. If we look up on the divide, this is Long Lake, and over here we've got Deep Lake. Off in the distance, Palouse Falls and the canyon, Palouse Canyon runs right over here, Palouse Falls and on down, Blue Mountain's off in the distance. But I want to concentrate here on Long Lake Canyon, because this is kind of the smoking gun of all this. At this point, the actual water flow was this direction, which means it was perpendicular to some of these canyons. And yet when you go down into the canyon, the Long Lake, you'll find that it's a very symmetrical canyon, or a canyon shape. And the only way you can really explain this with that water running left to right is that that rock had to be really fractured and easily plucked out of there as the floodwaters came over the top. I have come up with my own term to what to call this feature. Some people want to call them coulees. I don't call them coulees because they don't have the flat bottom, and they're really not a flood channel. It's not a valley, it's not a canyon, though it's canyon shaped. So I come up with my own term, and I call them fracture canyons. And in that respect, the Palouse Canyon itself is a fracture canyon, in my opinion. If you go a little bit further down, again, you were looking Palouse Canyon over here, left to right, and here we have the fracture on one side, and we're standing on the other side. This is Highway 261 taking you down to Palouse, or down to Lions Ferry. But if you notice over here, we've got another line coming through here. Kind of faint, but there it is. That is actually the Mullen Road. And if any of you know your history, the Mullen Road was constructed, started in 1859 to connect Fort Walla Walla with Fort Benton, Montana. And it crossed Lions Ferry and worked its way out of the canyon there and worked its way up across Washington Coulee and headed up Cow Creek. The Colville Military Road was also started in 1859, and those two roads share the same road between Fort Walla Walla and about 8 or 10 miles up Cow Creek from the confluence with the Palouse River, where the two divided, with the Colville Road continuing up Cow Creek to Sprague Lake and then heading north, and actually crosses Highway 2 between Reardon and Davenport. And we've got some other historical roads in the area, and these sometimes today, these are actually the highways you go on. Part of the road you head on down to the follows exactly the same route that the Mullen Road did. But there are places that they veer off, and when you've had a fire, they're a lot easier to find or to pick out. When there's a lot of overgrowth on it, they're disguised pretty good. So if we get down to the confluence of the Palouse and the Snake River, we have the Palouse River coming in right there, and the Snake River flowing south. But we've got all this water, not just coming out of the mouth where it is today, but we got this 10-mile wide stretch here where water's flowing over and spilling into the Snake River. There's so much water coming down here that some of it starts flowing up the Snake River. And it flows up to present-day Lewiston and continues up part of the Clearwater River, continues up the Snake River, and some of it even goes up part of the Grand Ronde River. There's just such a high volume of water here that it just starts spreading out both directions. There's so much water coming across that spills clear up to there. And we've got a couple of really neat little gravel bars here. The first one is called the Mid Canyon Bar. And you'll notice down the very bottom there, we've got a grain elevator, which is probably at least 100 feet high. And you'll also notice right behind it, we start seeing some of these giant ripple marks and current marks. And some of these are probably a good 40 feet in elevation height from the bottom to the top. Off in the distance, we've got another bar called Shoulder Bar. And this covers about a 1 square mile area up here of gravels. And the top of this bar is 500 feet above the valley floor. So that means that in this area, we had probably at least 600 feet of water covering this area right here when all these floodwaters came across. When Brett studied all this, I'm going to read just one sentence from one of his papers. He said, there is no more significant area than this divide for testing rival theories. And with these gravel bars and all the features we've looked at on the spillway up there on the divide, Brett's could explain every single one of them with his theory, but all the other theories couldn't. A little further down the river, Snake River, we have Devil's Canyon. Floaters is right over here, and this is another spillway across the divide. Again, this has got to be a fracture canyon to have such a straight line, and this parallels the Palouse Canyon. And you can also notice there's a little bit of spillway coming over the top as well. But you got Palouse soil right at the top too, so this had to really cut down in a hurry as that water spilled across. I want to share just a couple other features that we have on the divide, and these are potholes. And potholes are these circular basins in the basalt. Got another one down at the bottom, and this is Warschacht coulee running right across the bottom. So we're looking right up on the divide, and this is where you normally find these, is right along the edge of the coulee. And these are still kind of debatable as how these form. Let's look at that one up on top. There's North Point off in the distance to give you some bearing. This little hole is 350 feet, 51 feet deep and 82 feet in diameter, which means you can place an 8-story building in this thing. And how is it possible to get a hole like that in basalt rock? They're still debating that. You notice there's a little bit of a fracture right through here. So is it possible that there's some structure involved with it to get these things going? We know that when you get these huge floods, you start getting tornadic, like underwater tornadoes building up in them as that water starts spinning around in whirlpools. And we all know how destructive air tornadoes can be. So water tornadoes, you know, that tornadic action, that circling and that suction could start pulling some of these rocks out. And you ask, how do I know how big that is? Well, you met that young lady earlier on that erratic. Well, another guy that came with her was also a postgraduate student, and he was doing his work on potholes. And he'd been measuring potholes, and he had the equipment to measure these things. So both of them been over the Grand Coulee earlier in the week, and then they needed to come over in our area, and Chad was kind of a connection for him and wanted to know if I could find any erratics and potholes for him. I said, oh yeah, I can do that. So off we went on a hot August day to check out these potholes. And that's the three of them taking measurements, and they took hundreds and hundreds of measurements all around here, including the size of the rocks that they found inside. Here's that other pothole just off to the side. Here's Warschacht coulee, water moving right to left. I put a cow in there just to give you some scale. And again, we get the circular form, but then we've got this glob in the middle. And this isn't very common to see this in these potholes. If some of you are familiar with the Odessa craters, there's again, a lot of these round features up around Odessa, and they call them Odessa craters. And a lot of times they'll find dikes, circular dikes all the way around the outer edge. And again, there's several theories as how they form. It may be they're different ways, but up there they think that with these circular dikes that go around, which we don't have here, one of the theories is that as that lava flows out, it quickly cools on the top and forms a crust, which insulates it. And so the lava can keep flowing underneath it. And that's why that lava can flow for hundreds of miles, because it gets that protective crust on top. Well, if that lava flows through and kind of starts quitting, it might leave kind of a void underneath, and you may have a collapse that goes down. And the idea is as that collapses down, it cracks around the outer side of that circle, and then the lava comes out and forms that circular dike around it. What I'm thinking might have happened here is that same thing started, but instead of collapsing or cracking around the outer edge, it cracked in the middle, and some of that lava flowed back up through the very middle, forming that structure right there in the middle. And that being cooling at a different rate, different hardness, and it just resisted the erosion like the others. But that one's kind of different. And if you look just a little bit to the left there's Warschacht off to the side. Again, you get some more of these circular formations. You head down towards Warschacht, we've got another fracture canyon through here, but there's 3 potholes within it. So these things kind of working together. If we go up the coulee a little bit, here's Hooper off in the distance. Here we got another pothole. Almost as big as the other one, but not quite. And off in the distance, we've got another circular formation, which seems that it probably formed earlier and then it got truncated. And this one here is almost ready. One more flood, and this one might look more like this one here. We're going to go up right above Hooper here. And here's another one, really much different. It's much shallower and not quite as big in diameter. And there's other ones around it, but this is right where, you know, that those two bodies of water were coming together. There was a lot of turbulence there. Again, there's a couple of people standing right there for scale. So those are some of the features we have on the divide: fracture canyons and potholes. Well, we've kind of gone around and skirted all the way around the star of our show. So I think it's time to bring our star out. Palouse Falls is about midway in the Palouse Canyon. And it's basically going over a retreating cataract, which probably started down when the water first entered the Snake River, and it followed those fracture zones up. And it retreats at a rate of a fraction of an inch every year probably now, but during those big floods, it was retreating hundreds of yards at a time. It wasn't until a few years ago that we got a real accurate height of the waterfall. We'd always thought it was around, you'd see 186 to 200 feet. But some of you may have seen the video of the kayaker that actually kayaked over the falls. If you haven't seen it, you can go just Google in Palouse Falls and kayak, and you can actually watch the video of this idiot that successfully kayaked over the falls. He holds the world's record for the highest waterfall ever taken with a kayak. He had to come back and actually get a real measurement on it in order to get it entered in the book of records. There's only one other guy since him that has tried it. He made it across and survived, but he got separated from the kayak when he hit the water down at the bottom, so his didn't count. The guy that did it, all he did was break his wrist, but other than that, he was okay. Read an article about it afterwards, an interview he had, and he says he's not going to do it again. Once was enough. If you've been to Palouse Falls, you've probably come in the spring, right about now when the water's flowing really good. But if you're ever over this neck of the woods during the winter and it's been below freezing for a couple of weeks, I encourage you to go down to see it in the winter, because it's a whole different picture. Kind of like an ice castle down there. In fact, you almost need to visit in all 4 seasons to get the flavor of it. So with the sun setting in the west and night falling upon us, I'm going to end the program here and open it up for questions.
You're welcome again to type your question in the chat window, or you can hit your space bar and just ask.
Yeah, Lloyd, this is Malcolm.
Yeah.
Do you know, I guess, was the breach where the Palouse, you know, the change of flow cutting across and going into the Snake River, do we know what the timing was?
Of the floods?
Was it one flood, or was it maybe a couple of floods that?
Right now, the Friends of the Pleistocene have kind of finally agreed on how many floods there were from Lake Missoula during the last glaciation.
Mm-hmm.
And they figured there were just a few over 80 from Lake Missoula. About half of those made it to Portland. Half of them didn't get down that far.
Yeah.
They know that the first floods were the biggest ones, and over time, they became smaller. And that is because this all occurred right at the end of the last glacial period. And so when those ice dams were first forming, the ice was still coming and building up again and building up. But as time went on, it wasn't advancing as quickly, and you had more melting of ice and snow into Lake Missoula. So they figured those first lakes took about 120 years to form. But over time, it took down to only about 40 years to form. They were much smaller. That's why those smaller ones didn't make it all the way down. And we end up with that that point that, excuse me, the floods, the first one spread out over a large area as they came across it through the channel scablands. But over time, the floodwaters became less and less, but the channels they were going through, the coulees, were getting bigger and bigger. And so as you got less water and bigger coulees, they got more and more concentrated on the later ones.
So of these 80 floods, when is it thought that they started?
They
20?
figured now they started about 18,000 years ago. About 18,000 years ago was the first ones, and the last ones were around 14,000.
Oh, so it's quite a compressed period of time.
Yeah. But they figure, with 80 floods and you're going,
Yeah.
you figured out that's about where we're at.
Thanks.
Other questions?
There are questions in the chat.
I see one. One of them says, are any of the large potholes publicly accessible?
No. They're all on private ground. Little Palouse Falls is on private ground. The one above the Palouse River, you can actually see from Highway 26 if you know where to look. You can kind of just see it over there, but you can't really look down into it. But none of those potholes, and even that one down at the bottom of the coulee with the plug in it, you can actually see the plug from Highway 26 right along the base of the coulee.
We've got another question. What was the actual measured height of the falls?
It was 184 feet to 186 feet. Because this time of the year, there's probably about 184 feet from the top to the bottom, but when it starts flowing all the way across, you're another couple feet higher. So it varies depending on what time of the season it is. But most people are going around 184 feet. It is also the official state waterfall of Washington State.
There's a question from Thomas, and the question is, isn't there a volcanic vent or dike near the Eskier Ranch off Rock Creek?
Yes, there is. There's one there on the west side. And then there's another one up near Tokyo Junction on Interstate 90. I haven't seen that one. I think I've also found one on Cow Creek on the road between Benge and Ralston, right at Cow Creek, or almost at Cow Creek. I got to get a geologist in there to confirm that, but it sure looks like it. And that one hasn't been positively identified yet, but as we got more and more ice out there from local ranchers and farmers, they tell me about these things, and then I go out and look at them, but then I need to get a bona fide geologist in there to confirm it. But it looks like another possibility right there on Cow Creek. This is all fairly new, looking at this scoria, and as an indication of where these fissure eruptions were.
Other questions? I see one. What is the schedule for the IAFI Museum at La Crosse?
Well, that's a good question. Our chapter is co-sponsoring all that process up there. We did the official groundbreaking in September. That consists of 5 buildings that were made from rock, basalt rock, river rock, that was cut out by the Ice Age floods. La Crosse is located right on the eastern edge of the Palouse Scabland Tract, and it sits in a coulee. And the first people there, when they started building stuff, they had lots of rock, so they built 4 houses out of rock, actually 4 little bunk houses as well as a bigger house across the street. And they also built another building which became a gas station. And right now, one of those bunk houses is totally done now, and it's a temporary housing for our Ice Age Floods Museum. It's not very big, but that's what we've got. And after the groundbreaking, the other 3 little bunk houses, they had to take all the rocks off because they just got into so disrepair. But they took them down, poured new foundations, and they've got the structure up right now. They're ready to start putting the rock back on them. 2 of those are going to be bunk houses for housing for people who are coming through town and need to stay overnight. The middle one's going to be a bathroom area for both of them. The existing one we've got, once that moves into the new facility, which will be the gas station, it'll be a much bigger facility for our museum. That one will probably end up being used as a incubator or some other use for it. But we're progressing really big time now. Our chapter newsletter will get published on the IAFI website probably in about 2 or 3 weeks under our Palouse Falls chapter. And I've got an article in there about it and some pictures of where we're at on it. But we're pretty excited about that. And we sent our newsletter out to our own members first, then a few weeks later we put it on the website. But it'll show up there, and some of our other newsletters are on there, which also talk about the museum.
I see some questions missed early on. One of them is from Anne. She says, back to the erratics. Can you tell where the erratics came from?
To some degree you can. You know, you can match rock types with what you've got around northern Idaho, western Montana. So to a degree you can, but you're also limited because there's a lot of granite up there, and all we know for sure is it didn't come out of our area. It had to come in from up north.
Here's another one from Keith. And Keith is asking, did the young woman you showed on the slide, I'm assuming the one from UMass, eventually tell you the age of the granite erratic from her studies?
I'm anxiously waiting to hear back from her. I talked to her a year ago, and she was already off somewhere else doing some other studies, and she was finally getting her samples sent into the lab, but I hadn't heard back yet. But I'll keep pestering her because I really want to know what those results are. And once I got those, they'll be in our newsletter too. It'll be interesting to see if these erratics, you know, how they date compared to the ones in Grand Coulee.
And I see one more from way back at 725 from Jack. He says, we see so many basalt stones with streaks of white that are often at a 60-degree angle. Is this another sign of the associative nature of the magma that results in the polygonal shapes?
That's a good question. I don't know. The basalt rock, if you break open a basalt rock, it'll be almost black. But the basalt you see along the road is more of a gray color or brown color. And that's because one of the elements within that basalt is rust or iron, and it rusts once it gets exposed to the elements, and then it changes color. But it's kind of neat sometimes to see a basalt rock actually broken apart, and how, you know, it's pretty black. And right-hand side. But as far as those white streaks, I'm not familiar with those. Like I say, I consider myself an amateur geomorphologist, not a geologist.
Well, we'd like to thank you for coming and presenting for us all the way from Washtenaw. And let's show him our appreciation by putting our hands together, or if you prefer, by hitting the reaction button and clapping via the reactions. So again, Lloyd, thank you very much. Appreciate your willingness to share your knowledge of the Palouse Falls region.
I just wish I could have come in person.
Well, maybe next time.
All right, thank you.
All right. Good night, everybody.